Thank you very much. Thanks for having me as well. So I want to tell you today about the theoretical links between magnetars and fast radio bursts. We already heard yesterday a very nice talk about the observational links. Today I want to dig in a little bit into the theory. And I will start with some very general things we can say about the emission site and characteristics, physical characteristics at the emission region. So the first thing that we know about fast radio burst is that it's fast. It's very short in duration, and that immediately tells us that the region from which the energy is sourced has to be small. If you just take the light crossing time that is associated with the duration of an FRB, you get something like a few hundred kilometers. So the source has to be, the central engine from which the energy is sourced has to be smaller than that, and that suggests a neutron star or a black hole. Now, if you want to actually look not at the central engine, but at the emission site, the region from which the emission is created, there you have to be a bit more careful for two reasons. One thing is that this emission region could be moving relativistically, in which case you get an enhancement by a factor of 2 gamma squared compared to the previous estimate. And secondly, for reasons that I will not go into too much detail at the moment, the timescale you care about here is not the total duration of the burst, but the variability time. So anyway, you can do this estimate and you can see that it opens up some parameter space for different emission sites of the fast radio burst. Incidentally, if you look at the lateral size of the source, which we will touch on in a few slides, you see that it's decreased by a factor of gamma compared to the previous. So keep that in mind. Okay, now people who are familiar with gamma ray bursts will be familiar with the fact that when you have a relativistic shell that is expanding and emitting, you have a few different characteristic timescales that come up naturally. You have the timescale associated with the radio stability time. You have the timescale associated with the angular region that is visible to you as an observer when you take relativistic beaming into account. And you have the radial thickness of the shell. And as it turns out, there is a nice coincidence where all of these timescales are basically up to factors of order unity the same. They are R over 2C gamma squared. And this has interesting consequences in terms of the emission that we can expect to see from various models. And in particular, when we apply this to blast wave models, what it means is that you cannot have very temporally narrow or spectrally narrow features coming from such models without paying a huge cost in terms of efficiency. So to make the story very short, you can imagine this picture that you see over there on the right-hand side. If you have an emitting shell, even if it's emitting instantaneously and an infinitely narrow spectrum in the co-moving frame, what you will see in an observer frame is going to be smeary, because you will first see the photons coming directly towards you. They will be beamed the most, and later you will see photons coming from a higher latitude. They will be beamed less and arrive at a later time. So there is an unavoidable spectral width and temporal width of these bursts, and this is already something that is challenged by a lot of the data that we have, both the temporal variability and the spectral width. So this is one strong constraint about the emission site. The second thing I want to mention has to do with scintillation. This was already mentioned a few times so far in the conference, but the idea is the following, that back in 2023, we suggested that if you have a scattering screen in the host galaxy of the FRB source, then this screen can potentially resolve the emission site. So that means that if the projected size of the emission site is small compared to the diffraction length, you will see significant modulation. If it is large, you will see weaker modulation, and that in principle can put a limit on the size of the source. So indeed, we then collaborated with the CHIME team, and this was already shown a few times earlier. And the result is that the source size, the lateral source size, needs to be less than a few times 10 to the 4 kilometers, which is already very challenging for models such as the faraway. So let's go a bit deeper into the physical characteristics. So the first thing I want to do here is to mention that since we have this very high luminosity of the FRB, it means that the electromagnetic wave associated with the FRB is very strong. And for all models, at the place where you either emit the radiation or launch the disturbance that later on leads to the radiation, the magnetic field at that location needs to be at least as strong as that. This is true for basically all models. And that already tells you that the magnetic field needs to be very large at this launch point, large enough that we need to have a magnetic source. So we already said that the source is compact. Now we see that it's magnetic. The natural place to go is a neutron star. Neutron stars, or specifically pulsars, are objects that we know are highly magnetic, compact, and radiate in radio. So we might imagine that this is also the case for fast radio bursts. However, what I want to tell you is that this doesn't work. Okay, if we take a pulsar, it's very straightforward to calculate the luminosity that can come out of this, and it fails by orders of magnitude compared to the luminosity of a typical fast radio burst. There's some dependency of parameters here, which we took to be very conservative. We'll talk about the details later if you're interested. But the idea is that if you're using the rotational energy of the neutron star as your energy source, it doesn't work out because the energy does not come out quickly enough through dipole radiation. So instead, we need to rely on a different energy source, and the other natural energy source that we have in a neutron star is the magnetic energy. So if we rely on magnetic energy, let's see how much magnetic energy we actually need. So one way to look at that is to look at bursts that have been monitored for a long time. We saw some discussion of this yesterday as well. Here I will give the specific example of 121102, which in about 56 hours of concurrent observations with the fast released this amount of energy, isotopic equivalent. So then you can, since the source has been steady, since we know it basically, you can extrapolate this for some reasonable activity time, and you can see that the released energy comes out to be about 10 to the 45 Hertz, up to this factor of beaming over the efficiency. And you can then convert this to a magnetic field that is required, and you see that the magnetic field that is required for a neutron star is already at the level of several times 10 to the 13 Gauss, which is already magnetar level strength. So just from these simple arguments, we already come down to magnetars as the sources of these typical FRBs. Now, we have this factor of FB over efficiency, and this is an important point to consider. Yesterday, it was mentioned that if this beaming factor is order unity, we might already approach some kind of energy source in fast radio bursts, and maybe some of the most active sources are already challenging the magnetar energy. This is true only if the beaming factor is of order unity. However, there are some reasons to believe that this beaming factor effectively might be much less than 30, in which case we basically remove completely this energetic problem. And two factors can come into play here. One is that the emission site is the proliferation location on the surface of the neutron star. And second is if that location, which say is associated with the polar gap, as we know, for example, in pulsars, is aligned between the magnetic axis, which defines the polar gap, and the speed axis. And if those are also aligned with the observer line of sight, or more or less aligned with the observer line of sight, then the effective beaming is going to be tiny, and you remove the problem of the energetics. Now, take into account that if you just have beaming at random locations of the neutron star, then that alone is not enough, because the effective beaming will still be order unity. If you have bursts that are individually beamed, but they happen at random locations, then each burst, the true energy is much smaller than the isotopic equivalent to calculate, but you miss a huge fraction of bursts, and those two factors exactly compensate each other. However, if there is this preferential alignment uniactive, this does change significantly the beaming function. So we suggested this idea that the very active beam would be associated with aligned magnetars. There are several reasons that fit nicely the observations. One has to do with the energetics that I already mentioned. One has to do with the fact that we don't see periodicity in the lifetime data of the sources. Another has to do with the actually time fraction that we calculate what is the volumetric density of sources like those very active beams like 2024 0114A. They are tiny. They are about 1 billion compared to standard magnets. So we actually want something that is very pure. We don't want something unique. We want something that is very, very special. So this actually is good for that point of view. It even helps to explain the spectral temporal dichotomy that is in chambers between repeaters and non-repeaters, because you're essentially seeing a preferential viewpoint on the surface, static viewpoint on the surface of the neutron star. When you then go to non-repeaters, what we think is that these will be preferentially probably placed to have misalignment between the magnetic and spin axis. In this case, there is a natural time scale that starts out, which is the time scale that the polar cap sweeps across the observer. This time scale is naturally coming out at a few milliseconds with different parameters, and can explain things like polarization and swing, which was very nicely shown in the example that you see on the right. So you can maintain actual polarization by having tens of degrees change in a smooth way, much like in single pulsars, where you have this S-scale time space. So even moving beyond this geometrical interpretation, what we can do is we can ask, just looking at the data, is there a need at present to have multiple combinations to explain very active repeaters, some active repeaters, non-repeaters, etc. And what we showed in this paper was that basically from population point of view, there is currently no need for it. In fact, if you look at this diagram on the left, which is the empirical diagram, maybe how common sources are compared to how active they are, you see that there is almost an inverse relation between those two. And this is just coming directly from observation. And as it turns out, when you plug this in to calculation of expected rates and so on, you can reproduce all these different quantities that we see in terms of ratio of repeaters to non-repeaters, ratio of non-repeaters, overall number of parameters, the detected volume, etc., etc. Distance differences between repeaters and non-repeaters, repeaters will be slightly closer to non-repeaters, and so on. So two quick things before I move to the second part, because I know I don't have much time. One has to do with PRSs. So for PRSs, these are very interesting sources that tell us a lot about what's going on in terms of the physical nature of the source. The best case is the case of 1211-2, simply because we know that it's extremely compact. And once you know that it's extremely compact, that's very constraining. To make a long story short, it tells you that the supernova that created this limit cannot be too energetic, and that the neutron star that was born could not be too fast spinning, otherwise it would have injected too much energy into this limit and expanded it way too much by now. So this tells you that actually you need to have an under-energetic supernova, and you need to have there, in order to explain the energy density, very highly magnetic neutron star at the center to make this work. There are also predictions of this model, and specifically looking at higher and lower frequencies, we expect to see cutoffs, self-absorption and cooling frequency cutoffs, and this is the predictions that can be tested. I will very briefly mention this paper that is about to be on the archive, if it's not already on the archive, by Gupta, who is working with me and Pulak Mohapatra. This is about Faraday conversion in the magnetar wind that is surrounding a neutron star, and people involve Faraday conversion, the way to get circular polarization that we see sometimes in bursts. What I just want to point out quickly here is that it is not trivial for Faraday conversion to do the job. To do it, what you need is you need to have a very high fraction of electron positron in your atom. If your atom is dominated by electron proton, you only get a very tiny amount of conversion. So you need to find an environment that actually gives you electron proton, and the magnetar wave is one potential such environment. Okay, moving to the second part, which I will do super quickly. So I want to tell you about this latest work here. And what we did here was basically to try and take a step back and look at all sorts of different models for the emission of the fast microburst. And what we realized is that there is interesting about it. There are all sorts of different ways in which the energy can be sourced. And you can see them listed on the left. There are all sorts of different ways that the energy can be radiated, and you see it on the right. And in all different models, the energy at some point, most of the energy passes through now. And it turns out that this has very significant implications, and I will show them very quickly. So we have a natural scale of density in the neutron star, which is called the Kinetic density. The actual density can be larger than this by some factor, which we call the thermal simplicity, but it's limited. no more than a million or so. And then you can compare the actual energy you put into particles, the actual velocity you put into particles, into what you observe. And what you see here is that you miss by about 8 or 9 orders of magnitude. Some dependence on parameters, but again, none of this can alleviate this difference. This is different from pulsars. Okay, in pulsars, there is no such problem. You can do this, but this is not the case in FRB. So the conclusions are qualitatively different. Similarly, you can do this in terms of brightness temperature. Again, there's this 10 order of magnitude difference between what you would expect and what you actually get. And finally, the simplest way to look at this is in terms of the total energetics. Just calculate how much energy you have in an FRB, take into account the efficiency. Each particle has gamma x squared, as how many particles will be in, and it's way more than what you have in the entire universe. So this doesn't work on its own, and what it means is that the particles need to be reused again and again and again very quickly. The natural time scale of cooling extremely fast, much faster than the actual calculation, and you need to provide very strong acceleration, very strong electric field to keep accelerating the particles. If you need very strong electric field, that means you need to have strong magnetic field, which is the source, and that means that you need to be very close to the neutral star. Even if you start with a Magnetar-style magnetic field, this limits your initial value to a very basic extent to 10 centimeters in most cases, actually quite a difference. So I will not go into all these details. If you are interested, you can compare. You basically discover all the different types of modules, hemispheric, connection, monster shocks, etc. They all run into severe problems with this kind of arguments. And what we find that survives is this family of models. It's not only one model that involves very fast acceleration at the emission star, and with the emission taking place very close to the neutral star. There's distance of 10 centimeters will be closer. So that is basically all. I leave you with my conclusion. Yeah. Yes. So basically, what you have, since you're viewing onto the polar cap, I will get the slide and then tell you. Okay. So this is a top-down view onto the polar cap. So this blue circle is the polar cap, and it's rotating. But it's rotating. Its center is rotating in this small red circle around the rotation axis. So if you're viewing at the 0 point here, you're basically always within view of the polar cap. So you're always in a situation where you could see vertices if vertices are coming from the polar cap.
Yeah, thanks for the very thanks for the very about yeah, I just wanted to note that when we look at the line losing pulsars, they seem to be weird in critical sense, which is very regional mission. And there is some connection there with the line. Working with 634, basically have very information where it's very unusual from those connections involved in the pulsars.
I'm not seeing these data, so we'll just talk about that.
More on the ones words and the ones you know, and people what you are asking, and what kind of people good stuff, and the factors for the audience.
Okay, so this is about the PLS. And basically, the limits, the main limits of the PLS come to two things. One is the energy density, which is huge. Just to account for the energy density, you need to have a Magnetar field, and you need to be dissipating this energy, as we know that on a relatively short time scale, actually short compared to what we know from the electric planets. So again, it's okay when we're talking about extreme short when we're talking about regulated movement. But this is something to keep in mind. And the other thing is that the supernova quantum field will be just because otherwise it would be expanded. Now, probably this is not a coincidence. Probably these issues are related to like something systemic related to the FRB producer. It doesn't mean that all FRB producers need to be as extreme as the FRB ever, but it's kind of the tip of the iceberg.
Thank you for Michael. For the Magnetar, we can add you mentioned here.
Wait.
Sorry. I wonder what ways we try to observe if we can happening in our
Okay, so the specific frequencies for patterns of the staff indicator, from what I thought, we need to go to a few tens of gigahertz to see the cooling rate, something like that. And to see the self-absorption and turnover, need to go down to maybe around 100 megahertz. We can look at this. So I got the first part you were asking about the polarization and changes, rapid polarization changes to see and repeaters. And this is something that can happen not just for the emission reason, that will be polarization or switching that will lead to slow rapid changes in polarization. And we do have some sources that this nasty, so that certainly has to be part of the picture. Plus, it could also give information effects as the one that's the second possibility. What was your second question? Okay, we can go ahead.
Oh, let's ask a question.
So good morning, everyone. I'm Pulak, and today I'll be talking about the repeating FRBs, and I'll be talking about whether we can use them to somehow bridge the gap between the two FRB populations. So the dichotomy of the fast radio bursts have been a burning topic of discussion since the discovery of the first repeater itself, and it has clearly divided the community into taking sides. And if you just take a look at the last year's poll at FRB 2025, you can see that there is clearly no consensus in the field about whether they are the same underlying population or they represent two distinct populations. So the fast radio bursts are broadly classified into repeaters and apparent one-offs, and to understand whether this dichotomy is real, we need to do rigorous population-wide studies. So what do we currently know about these populations? If we take a look at the burst rate distributions, the energy distributions, as well as the host galaxy environments, both the populations are more or less consistent with each other. However, the DM distribution seems to be different, which could be due to an observational bias. However, the stark morphological difference generally prevents people from unifying these two populations into one, where the repeating FRBs are generally seen to be wider in time and narrower in frequency. Repeating FRBs are generally show band limited emission as compared to the non-repeating ones, which are fairly broadband. Moreover, the non-repeaters are generally brighter and lack complex features such as downwards subburst drifting. Recently, in a study by Sanatol 2026, they identified a group of atypical repeaters, which are repeaters with generally with low burst rates and show morphological similarities to that to the non-repeaters. And this sort of led to the hypothesis that we'll be testing in this work, that what if the repeaters and non-repeaters are actually from the same population with morphological parameters evolving as a function of the burst rate. So previously there have been attempts by various groups to establish this correlation, especially between the burst rate and the width, and they have largely been unsuccessful. I'll briefly touch upon this at the end. And for this work, we are sticking to the CHIME FRB catalog 2 only. To evaluate the burst rate, we have used a simplistic method, and we have not done any fluence threshold scaling, as it depends on an arbitrary power law energy distribution index. And we are checking for the correlation of the width, bandwidth, spectral running, spectral index, peak flux, and the fluence with the burst rate. And we have done this analysis on the parameters obtained per individual subburst. So typically when you have a case like this where you have multiple repeating FRBs, and each repeating FRB has a unique burst rate, and per repeating FRB there are multiple bursts with different morphologies. So there is clearly this hierarchical structure in this data set, which lets us ask the question that what is the optimum way to evaluate the correlation. So there are generally two ways that people use. One is the complete pooling, where you pool all the bursts together and then try to evaluate the correlation. But the point is that all the bursts are not independent, and the trend will be dominated by hyperactive repeaters. The other method, which is slightly more reasonable, is that you don't do any pooling, and if you include the standard deviation of the repeating groups, you can actually sort of account for the intrinsic scatter. But this is unreliable for small sample sizes, especially for the case that we have where there are a lot of repeating FRBs with low burst counts. So to solve this issue, I will discuss about the methodology, which is the linear mixed models, which we have used in this work, which instead of doing complete pooling or no pooling at all, it does something known as a partial pooling using shrinkage. So if you take a look at the equation here, the first few terms here represent the typical linear regression. The beauty of the mixed model comes with the introduction of this term here, which is the random intercept. It is in a way describes how the different repeating groups vary from each other. So this sort of is a metric to understand what is the scatter between two repeating groups. And then there is this term which represents the intrinsic scatter from burst to burst. So I'm happy to discuss about this later in greater detail. So to account for the outliers, since we have a lot of outliers in the data, we have used a student T distribution, which allows for heavy tails. And it has a parameter nu, which controls the tail heaviness with nu greater than 30, implying it's a Gaussian, and lower nu values implying that the tails are heavy. And we have used a Bayesian hierarchical model using PyMC to carry out the Bayesian inference. Here are the results. If you focus on the top left panel, the x-axis is the burst rate, the y-axis is the width. The red points here denote the median per repeating group, and the blue points here represent the individual bursts. The black line is the best fit, and the dark gray line is the uncertainty on the best fit, and the light gray line is the intrinsic scatter that we get from the student T distribution. Now, if you take a look at the values quoted over here, the beta is the slope of the line along with the uncertainties, and the term next to it represents the probability of direction, which means that for what fraction of time the slope was, say, the posterior of the slope was positive or negative. And here we can see that for parameters such as width, we do see a positive correlation. And for parameters such as the spectral running and bandwidth, we see a negative correlation, and the same goes with the peak flux. Now, the next natural thing to ask is, can all the non-repeaters follow this trend, and does this trend really imply anything? So the point that we're trying to make here is that to find out what fraction of the non-repeaters are actually consistent with this trend line along with the scatter, given the uncertainty on the measured parameters. To do so, we draw 8,000 parameter sets from the Bayesian posterior. We calculate the 1 sigma predictive interval for each draw, and then we test if a non-repeater along with its observational errors fall within this interval or not. And if it matches in greater than 50% of the draws, we say that the source is statistically consistent with the repeater trend. The number 50% is arbitrary here and can be different values can be taken here, but this does not affect the inference of our results. So if we just plot the fraction of the iterations where the y observed is consistent with the non-repeater is consistent with the trend line, we see this bimodality in almost all the cases. If you take a look at the points here, which 0, which means that these non-repeaters never coincide with the best fit trend line within 1 sigma. And if you take a look at these non-repeaters, these are the ones which are always consistent with the 1 sigma trend line. Now, to compare whether these numbers are consistent or not, we did the same analysis with all the repeater bursts, and then we observed the following thing. Here, the green ones are the histograms for the non-repeaters, and the blue ones are the histogram for the repeaters. And we can see for almost all the properties except for the spectral running, we see that the distributions are more or less similar. And for the spectral running, we can see that the non-repeaters are more consistent with the trend line as compared to the repeaters. This is most likely because the intrinsic spread of the spectral running parameter within the repeaters is much larger. So before summarizing, I would like to just spend some time on the limitation and the points that we should be careful about. So firstly, I would like to briefly touch upon why did we find a correlation where the other published work has not yet found any correlation. We believe it could be a mixture of the methodology that we have used, which is different from the ones generally used in the literature, and the cuts that we have used are fairly relaxed as compared to the previous studies. And this brings me to the potential major limitations of this work, which is that since we have used the exposure times from the CHIME second catalog, the uncertainties are large, and we cannot firstly localize whether these bursts are beyond the FWHM of the formed beam or not, as well as we have used Gaussian uncertainties on the exposure time, which is generally not a good idea with these large uncertainties. Moreover, if a burst is detected in the grating lobe, we observe that the spectral and energy parameters are said to be contaminated. So the results about the spectral and energy parameters should be taken with a pinch of salt. And finally, we have not done a full fluence threshold scaling yet, which can corrupt the burst rate estimates. Although we did a quick check and we see that we still find a significant correlation there. So maybe the baseband catalog could come to the rescue. So to summarize, there is an apparent dichotomy in the FRB population, which is not very well understood. And we are trying to explore an hypothesis where the morphology is evolving as a function of the burst rate, as morphology has been one of the driving factors in separating these two into separate classes. We have used linear mixed models where we find that the burst rate is correlated with the temporal, spectral, and energetic properties. So here is a rough schematic summary of what we found out. We noticed that as the burst rate increases, the width increases, the bandwidth decreases, and the peak flux decreases. And if we vaguely say that the repeaters lie on the higher burst rate side on an average as compared to the one-offs, the morphological differences between the repeaters and non-repeaters can generally be described by this framework. And we also find that the non-repeater population is fairly consistent with this trend. Physically, this can be an interplay of the beaming angle, the beaming geometry, as well as the Lorentz factor. And as Paz was mentioning moments ago, that the non-repeaters can be interpreted as misaligned rotators. And in this framework, this kind of correlation is expected. So I would like to thank you all. Questions or comments are welcome. Thank you.
Okay. Hello, everyone. Thanks to the organizers for having me here to talk about the latest insights into the radio polarization catalog from the CHIME Baseband Catalog 2. And as Pulak was crying for the BaseCat 2, I mean, just kidding about that. But I want to start off with talking about BaseCat 2 itself. So this is undergoing full collaborative review at the moment, and this is for numbers. We have 2086 FRBs, as Mawson was proving yesterday, from December 2018. Oh, using this mic? Okay, is this better? Okay, thank you. I'll start again from the slide. So I'm talking about BaseCat 2 from the numbers itself, from December 2018 through to September 2023, with the full 2.56 microsecond time resolution, with median localization of half an arc minute. And similarly to BaseCat 1, the beamformed files, the finalized files, will be available publicly, similar to BaseCat 1, available post-acceptance of the paper. And we hope to get this out sometime. Well, the paper is undergoing full collaborative review